Previously, in real analysis, we have studied convergence of a sequence. Now here we are going to discuss convergence of infinite series, and we are going to begin with convergence of infinite series with positive terms. Now let un be a given sequence. So we have this sequence given by this term un. Infinite series of the sequence, it is given by this summation n varies from 1 to infinite un, which for brevity sometimes we are going to write as simply this summation un, and this is nothing but this is sum of all the infinite terms in this sequence. So this series, it is called as infinite series. Now with the sequence un, we can associate another sequence, and we'll write the sequence as this Sn, and this Sn is defined as sum of first n terms of this sequence un. Now here, sum of first n terms, it is called as partial sum. So this sequence Sn, it is called as sequence of partial sums. Now if the sequence of partial sums, it converges, then we say this series summation un, it converges, and suppose it converges to some value, say s, and if this sequence of partial sums Sn, it diverges, then we'll say this series summation un, it is going to diverge. So in this video, we'll be discussing convergence and divergence of infinite series. Now we take an example. Suppose we have this series which is given by this summation n varies from 1 to infinite 1 upon n plus 1 n plus 2. So we have this infinite series. Now the sequence corresponding to this series, it'll have its nth term as 1 upon n plus 1 n plus 2. Now what we'll do is we'll split this in two parts, taking these two together and these two together, and difference between n and n plus 2 is 2. So we'll write this as 1 by 2 and then 2 upon n plus 1 n plus 2, and we can write this as 1 by 2, and it will be n plus 2 minus n upon n plus 1 n plus 2. Now we split it in two parts. Here n plus 2 will cancel, so it will be 1 upon n plus 1, and minus here this n will cancel and will be 1 upon n plus 1 n plus 2. So that's our nth term for the sequence un. Now if we write its partial sum Sn, it will be given by u1 plus u2 up to un. Now it will be this 1 by 2. If we put n as 1, it will be this 1 2 minus 2 into 3. Now the second term it will be 1 upon, here the value of n is 2 now, so it will be this 2 3 minus 3 into 4, and will continue up to 1 by 2 1 upon n plus 1 minus 1 upon n plus 1 n plus 2. Now here these terms, they'll get cancelled, so we can write this Sn as 1 by 2, and it will be this 1 by 2 minus 1 upon n plus 1 n plus 2. Now if we take this limit n tends to infinite, this expression, it goes to 0. So limit of the sequence Sn, it is 1 by 4. So that means this sequence Sn, it converges, and it converges to this sum 1 by 4 And therefore, this series summation n varies from 1 to infinite 1 upon n, n plus 1, n plus 2, it is going to converge. So we can associate an infinite series with sequence of partial sums, and we can work out convergence of the series from convergence of the sequence of partial sums. Now, before we begin our discussion on various tests to find convergence of series, there are two theorems that we must know. And theorem 1 is the replacement, addition or omission of finite number of terms from this infinite series has no effect on convergence. So if we have any infinite series, summation un, if we add, replace or omit finite number of terms from this infinite series, it will not change the nature of convergence of the series. And the second theorem is, if each term of the series is multiplied by a non-zero number, then also convergence of the series remain unchanged. So these are the two theorems which we are going to need while discussing convergence of infinite series. Now we're going to begin with convergence of infinite series with positive terms. So here we have this series summation un, and here each of ui is greater than 0. And since each of ui is greater than 0, so this sequence of partial sums Sn, it is u1 plus u2 plus un, and each time we are adding some positive number to it. So this sequence, it is an increasing sequence. So for this infinite series with positive terms, sequence of partial sums, it will be a monotone sequence. Now for an infinite series, there is a necessary condition that must be followed for the convergence. And the necessary condition is, if this series summation un, or rather the summation n varies from 1 to infinite un, it converges, then this limit n tends to infinite un, it must be 0. Now you have to keep this in mind. This is neither a sufficient condition and nor it is true vice versa. So while solving questions for infinite series with positive terms, there will be many cases where you can straight away say the series diverges because this limit n tends to infinite un, it is unequal to 0. Say for example, we have this series under root of 1 by 4 plus under root of 2 by 6 plus under root of n by 2 into n plus 1, and it goes all the way up to infinite. Now this is your un. Now if we look at this limit n tends to infinite un, it will be this limit n tends to infinite under root of n upon 2 n plus 1. Now this is an infinite limit. Coefficient of n in the numerator is 1 and the denominator is 2. So value of this limit will be simply 1 by root 2, and which is unequal to 0. And since this limit n tends to infinite un equals to 0, it is a necessary condition. That means this series, it cannot converge. That is, this series, it is going to diverge. If we take another example, suppose we have to check for convergence of the series, which is summation n varies from 1 to infinite 1 by n to the power 1 by n. Now nth term for the sequence is 1 by n to the power 1 by n. Now we'll find this limit n tends to infinite un, and will be this limit n tends to infinite 1 upon n to the power 1 upon n. Now this is 0 to the power 0 form. Now we're going to write this as e to the power this limit n tends to infinite 1 by n log 1 by n, and we can write this as e to the power this limit n tends to infinite minus log n upon n, which is infinity upon infinity form. Now we can use L'Hopital's rule. So it will be this e to the power limit n tends to infinite. Now this is minus 1 by n upon 1. So it will be e to the power 0 and e to the power 0 is 1, which is unequal to 0. So this limit n tends to infinite un, it is not equal to 0. That means this series, it does not converge. Now for this convergence of positive term series, there are certain theorems. And the first theorem is the necessary and sufficient condition for the convergence of a positive term series summation un is that the sequence Sn of partial sums defined by this Sn equals u1 plus u2 plus un is bounded above. Now this gives weight to our second theorem, and which is a series of positive terms is divergent if each term after a fixed stage is greater than some fixed positive number. So if the series is not bounded above, then in that case, this infinite series of positive terms will be a divergent series. Now this third theorem is, suppose we have two infinite series of positive terms, say summation un and summation vn, where the series summation vn, it is convergent, and if each corresponding term of this series summation un, it is less than vn, then we'll say this series summation un will also converge. And in the same way, if we have two infinite series summation un and summation vn, and now this summation vn, it is a divergent series, and each corresponding term of un is greater than each corresponding term of vn, then we'll say this summation un, it is going to diverge. So basically this is comparison test. So we are going to work out convergence of one series by comparing it with convergence of another series. Now this fourth theorem is, if we have two converging series summation un and summation vn, then summation un plus minus vn will also be a convergent series. So if we add or subtract two convergent series, then the resulting series will also be a converging series. And finally, this fifth theorem, and which is, if un converges and summation vn diverges, then this sum un plus vn, it is going to diverge. So we are going to use these theorems for comparison test, and in addition to these theorems, we have this condition that a necessary condition for convergence of infinite series is this limit n tends to infinite un, it must be 0, and if it is unequal to 0, then the series cannot converge. Now before we are going to use these theorems for convergence, there are two important standard series that we must know, and the first one is this summation r to the power n. Now this is r plus r square plus r cube r to the power n up to infinite. Now this is nothing but an infinite GP. Now since we are discussing infinite series with positive terms, so we can say this summation Rn, it is going to converge if r is less than 1, and it will diverge if r is greater than or equal to 1. And the second important standard series is lambda series or generalized harmonic series. We can write the series as this summation 1 upon n to the power lambda, where n varies from 1 to infinite. Now if lambda is greater than 1, then this series, it converges, and if lambda is less than or equal to 1, then this series, it diverges. Now we take lambda as 1, then this series, it becomes harmonic series. So it will be this summation n varies from 1 to infinite, 1 upon n, which is 1 plus 1 by 2 plus 1 by 3 plus 1 by n up to infinite, and we know this series, it diverges. And if lambda is less than 1 also, say for example, lambda is 1 by 2, then we can write this series as this summation n varies from 1 to infinite 1 upon under root n, and will be 1 plus 1 upon root 2 plus 1 upon root 3 plus 1 upon root n will also diverge. But if lambda is greater than 1, say for example, lambda equals 2, then we can write this series as 1 upon n square. So it will be 1 plus 1 upon 2 square plus 1 upon 3 square plus 1 upon n square up to infinite. And this series is going to converge. Actually, this problem, it is a very famous problem, and it goes by the name the Bessel problem. And we have already proved that sum of the series is pi square by 6. If you are interested in solution to this Bessel problem, I'll provide the link to that video in the description below. So we are going to use these two standard series for determining convergence of series. First one is your infinite GP, and the second one is your generalized harmonic series. So now we'll begin our discussion of different tests of convergence. And the first one is comparison test of the first kind. First kind or first type. So here we are going to compare the two series to test for convergence and to test for divergence. So if we have to test for convergence of this series, summation un, then we'll take another converging series Vn such that each corresponding term of un is less than or equal to Vn for all n greater than or equal to some number m. So for a natural number m, we have un less than equal to Vn for all n which are greater than or equal to m. And if we have to test for divergence, so if we have to test for divergence of un, then we'll take a divergent series Vn such that there exists a natural number m for which corresponding term of un will be greater than or equal to Vn for all n greater than or equal to m. So if corresponding term of un is less than or equal to corresponding term of Vn, where Vn is a convergent series, then this series it converges. And if corresponding term of un is greater than corresponding term of Vn for a divergent series Vn, then this series Vn it diverges. Since both the series they contain positive term, so we can write this first one as un upon Vn is less than or equal to 1, and the second one is un upon Vn it is greater than or equal to 1. So rather than comparing the two series, what we'll do is we'll use something called as practical comparison test for the first type. Now in practical comparison test of the first type, we'll work out this limit n tends to infinite un upon Vn it is equal to L, and if it is unequal to 0, then both the series summation un and summation Vn, they'll have identical behavior to convergence. So if this series Vn converges, then un will converge, and if Vn diverges, then this summation un will also diverge. So rather than comparing the two terms, we'll simply work out this limit n tends to infinite un upon Vn. If it is unequal to 0, then we'll say both the series they'll have identical behavior of convergence. Now say for example, we have to test for the convergence of this series 1 upon n square plus 1. So that's our summation un. So in this case, un is 1 upon n square plus 1. Now corresponding to it, we'll take another series which is summation 1 upon n square Now this is nothing but this is generalized harmonic series where the value of lambda is greater than 1. Now we already know this series, it converges. And in this case, Vn, it is 1 upon n square. Now if we take this limit, n tends to infinite, un upon Vn will be this limit, n tends to infinite. Now un is 1 upon n square plus 1 divided by 1 upon n square. So it will be this limit, n tends to infinite, n square upon n square plus 1. Now here it is an infinite limit. Highest power of n is 2. Coefficient of n square is 1 in the numerator and 1 in the denominator. So it is 1, and which is unequal to 0. That means this series summation 1 upon n square plus 1 will also converge. Because both the series, they'll have identical behavior to convergence. Now let us take another example. Suppose we have to find convergence of this series, summation under root of n upon n to the power 4 plus a to the power 4. Now here we know it is effectively 1 upon under root of n cube, so it will be n to the power 3 by 2. So we'll compare it with this series, summation 1 upon n to the power 3 by 2. And since lambda is greater than 1, we know this n to the power 3 by 2, it converges. Now again, we'll find this limit n tends to infinite, un upon Vn, so it will be this limit, n tends to infinite. Now this is n to the power 1 by 2 under root of n to the power 4 plus a to the power 4 upon 1 upon n to the power 3 by 2. Now it will be this limit, n tends to infinite, n square upon under root of n to the power 4 plus a to the power 4. Now here, highest power of n in the numerator is 2, and in the denominator also it is 2. So answer to this limit will be coefficient of n square, and which is 1, and it is unequal to 0. And since this second series, it converges, it means this series under root n upon n to the power 4 plus a to the power 4 will also converge. Now let us take another example. This summation n upon n square plus 3. Now this is effectively 1 by n. So we'll compare it with this series 1 upon 1 by n, which is harmonic series, and we know harmonic series, it diverges. Now we find this limit, n tends to infinite, un upon Vn, so it will be this n upon n square plus 3 upon 1 by n, which is this limit, n tends to infinite, n square upon n square plus 3, and it is equal to 1, which is unequal to 0. Now both the series, they'll have same behavior of convergence. So if this summation 1 by n diverges, this series summation n upon n square plus 3 will also diverge. Now we take some examples where we want to compare it with geometric series. Say for example, we are given this series summation 1 upon n to the power n. Now we know that for any n greater than 2, n to the power n will be greater than 2 to the power n, and we have omitted first two terms. And if we recall theorem 1, it says omission of finite number of terms, it does not change the behavior of convergence of a series. Now 1 upon n to the power n will be less than 1 upon 2 to the power n. So we have to write this second series as this summation 1 upon 2 to the power n. Now this summation 1 upon 2 to the power n, it is an infinite GP with common ratio 1 by 2, and therefore this series, it converges. And we have 1 upon n to the power n, which is less than 1 upon 2 to the power n for any n greater than 2. That means from comparison test, we can say this series 1 upon n to the power n, it also converges.